Now let's look at the another problem where we try to search the insert position in a given sorted array. So as part of this problem statement, what we will be given is, we will be given a sorted array of distinct integers. Remember that we will be given an array in which all the values are distinct and the array is sorted. And along with that, we will also be given a target value, and we need to return the index of the target if it is found in the array of values whatever we have been given. If the target value is found, we need to return it, the index at which it is found. If it is not found, then what we need to do, then return the index where it would be if it were inserted in the order. That means that we have to insert the target value into the sorted array. Basically, we need to find the position at which we can insert the target value into that sorted array such that the array will still remain a sorted array. And you must write an algorithm to algorithm with order of log n runtime complexity. So that is the example, that is the problem statement that we have gotten here. Here the array of values that we have gotten is 1, 4, 5, 7, 8, right? And if you see, these values are sorted in the ascending order. One more thing that you need to understand is the values of array are sorted in the ascending order here. So if at all, if your problem statement mentions that the array is sorted in the descending order, you can follow the exact logic that we are writing, but one or two conditions that we need to interchange, that I will tell you when I write the algorithm. But anyway, here the target that I want to insert is 5. Now if you look here, right, the array has the value 5 already at index 2. Since the value is already found, I need to return the index 2 because 5 is already found. And similarly, if you look here, another array of values that we have gotten is 1, 3, 4, 5, and the target is 2. And we need to insert this 2 into sorted array, right? So where we can insert this 2 into the sorted array such that the array still remains sorted? At index 1. Basically at the position of 3 we can insert 1, and 3, 4, 5 we can move to right by 1 position so that the array will still remain sorted. That means the resulting array will be 1, 2, 3, 4, 5. Okay. Similarly, if you look at here, 1, 2, 3, 4 is the example, and the target value is 7, and we can insert it after 4. So the index is 4. So the resulting array will be 1, 2, 3, 4, 7 after insertion. But we don't have to return the resulting array. Rather, we want to return the index where we can insert the value. Okay, if at all the value is found, just like in this example, we have to return the index at which the value is found. Okay, so that is the problem statement that we have got. Even though the problem statement mentions that we should be writing the solution in order of log n time, I'll be explaining the brute force approach as well as the effective approach after completing the brute force implementation. Okay, now anyway, let's go ahead and check the brute force approach. Alright, now here let's take this example, right? These are the array of values and the target value is 6. Now let's try to understand how can we apply the brute force approach to solve this specific problem. So brute force approach is very simple, right? Let's just say the target value given is 5. For now, let's just assume that we have been given 5. So what we can do, we can start the iteration from index 0, and we will pick up every value and we will compare the value at any index. If the value is matching with the target value, we can return that index itself. If not, then what we can do, any value that we are picking from a particular index, if it is greater than the target that we have gotten, then that is the position where we can insert. So for this, the brute force approach will be, we will be simply running a loop from 0 till the length of the array, basically till the last index. So immediately what we will do, if at all the value at this ith index is equal to the given target value, then we will immediately return the index itself, because at that index we found the value. If this is not the case, another scenario is if the value at ith index is greater than the target, that means we have already compared the previous values, right? Previous index values. So ith index value is more. So this is where we need to insert because target is smaller than that. So here we can immediately return ith index itself. Okay, so this is the simple brute force implementation. Okay, just to imagine the worst case scenario to understand the time complexities and space complexities. Here we have let's just assume the target we have gotten is, let's just say 11. Now what is going to happen? We have to start iterating from index 0 till the very last index, and the amount of time it is going to take will be order of n, because we have to reach till n. Okay, so that is one thing. And another scenario that I can think of, that we have to handle after this for loop is, let's just say if we are inserting 11 is something that we couldn't insert inside this index, inside this logic, right? If at all, if we return a value from this for loop, then well and good. If we are not returning anything, that value should go in the end, right? That is the reason why in the end we will return the length of the array, because 11 is something that should be inserted at index 6. So length of the array is nothing but 6, right? So 6 should be returned. So after the for loop completion, if we don't return anything in the for loop, we need to return it outside the for loop. So this is one case I missed while explaining, but while understanding the time complexity, I got to know the scenario, so I quickly return that. But anyway, the time complexity of this would be order of n, and the space complexity will be order of 1, because we are simply trying to find the index. Now let's try to dry run it for the index, for the target value 6. So we will go to index 0. Index 0 has the value 1, which is smaller than the target value. So immediately we will move on to the next index. So index 1 has 4, we have 6. So 4 is smaller than 6. So immediately we will move on to the next index again. 5 and 6 we have, again smaller. So immediately we will move on to the next index. So here the value is 7 and the value we have is 6. So 7 is greater than 6. So we need to return index 3 as output, and 3 is where we need to insert 6, so that all other values will still remain in the sorted order. If at all, if you have gotten 5, what will happen? We will reach till index 2. At index 2, this condition will match. So immediately we will return index 2 as output. Okay, so this is the simple brute force, logic to understand the problem that we have gotten. Now, remember that the array that we have gotten is sorted in the ascending order, right? And ultimately, we need to find the position at which the value is found, or the value need to be inserted. So that is the logic. But whenever the array is sorted, we can apply the binary searching algorithm, right? So that is where we will bring down the time complexity of this from order of log n to order of n to order of log n. Now let's just dive into binary searching technique and understand the process behind finding the insert position. Now let's dive into binary search specific approach for solving this problem. So here, the implementation is exactly similar to binary searching algorithm, but remember that in the case of binary searching algorithm, we will have start variable and end variable, right? So ultimately, we will calculate the middle. At any given point of time, if the middle index has the value which is same as that of target, we will immediately return the middle index. Otherwise, after checking all the possibilities, once the iterative logic is completed, whatever the start index that we have, this start index variable will hold the position in which we can insert the target value. So that is the aim here. So just like any traditional non-tweaked binary searching algorithm, what we will do, we will initialize the start and end with, start with 0, end with the last index we have in the array, and this will become our search span. Immediately what we will do, we will calculate the middle. 0 plus 5 divided by 2, which is 2.5. So if we floor it, we will get 2. So the middle is nothing but index 2. At index 2 we have 5, but the value we want to insert is 6. That means it should be after index 2, because index 2 has 5. 6 should be after 5, right? So our search range will become, immediately we will update the start with middle plus 1. So this will be our new start, and this will be the end, whatever we have. Again, what we will do, we will calculate the middle. Now the middle is nothing but 3 plus 5 divided by 2, which is nothing but 4, and index 4 is where we have got in the middle. At index 4 we have the value 8, but the value we are looking to insert is 6. That means 8 should be, 6 is smaller. That means 6 should be on the left side of 8. So immediately what we will do is, we will update the end with middle minus 1. So at this point of time, both start and end are at the same position. Because we had 4, we updated the end with 4 minus 1, which is 3. Now again we will calculate the middle, and what is going to happen? 3 plus 3 by 2, which is nothing but 6 by 2, which is nothing but 3, and middle also we have gotten the same, and we have value 7, and the value 7 is greater than 6. That means it should be inserted on the left side. So what we will do, immediately we will update the end with middle minus 1, that means to index 2. Now start is at index 3 and end is at index 2. That means start is greater than end is less than start, otherwise start is greater than end, right? So at this point of time, we know we cannot compare the values, so immediately we can stop. Now at this point of time, start is at index 3, right? This 3 is where we can insert the value 6. If you observe, if we insert it, then the resulting will be 1 4 5 6 7 8 10. So this is the resulting array. So this start variable will hold after all the possibilities, all the search ranges that we have to search. Whatever the start variable we have, it will hold the reference of the basically the index at which the target value can be inserted. Okay, so that is the understanding. Now let's just try to understand the same algorithm where the value is already present. Let's just say we are trying to insert the value 4 into the array. So the 4 value is already present, right? But anyway, let's try to dry run it. Start is at index 0 and end is at index 5 in the beginning. So this will become our search range. So we will calculate the middle. 0 plus 5 by 2, 2.5. If we floor it, we get 2. Index 2 is where we have the middle at index 2. At index 2 we have the value 5, and the value we want to insert is 4. So it should be anywhere on the left side. So immediately what we will do, we will update the end with middle minus 1. So here the end will come, start is at 0 and end is at index 1. Again we will calculate the, what we will do, we will calculate the middle, 0.5. If we floor it, we will get 0. So at index 0, what value we have? 1. But the value we want to insert is 4. 4 should be on the right? So immediately what we will do, we will update the start to middle plus 1, which is at index 1. Now again we will calculate the middle, 1 plus 1 divided by 2, which is 1. At index 1, we have the value 4, and the value we also want to insert is also 4 itself. That means the value is already found, right? We can simply compare, right? Before we move on to either left side or right side, we can also check for the equals case in binary searching technique, right? So the index 1 has the value 4. So immediately, since the value is already found, we will immediately return index 1, which is nothing but the middle value. Okay, so these are all the scenarios that we can cover with this implementation. Okay, now let's just quickly write the pseudo code for the algorithm that we have discussed. So we will write one function called find insert position. What it does, it will take the nums array and it will also take the target. So inside that, what we will do, we will basically check start index. We will initialize start index with 0, and we will initialize the end index with length of the nums array minus 1, because we need to initialize it with a valid last index. Along with that, we will initialize one more variable middle, initialize it with minus 1. Immediately what we will do, we will run a loop as long as start is less than or equal to end. What we will do, we will calculate the middle with start plus end divided by 2. Once we get that, there are few scenarios, right? Either move on to the left part or right part, or check the equals value. So immediately check if the nums of mid is equal to the given target, immediately return the middle itself, because the value is already found and we can immediately return. If this is not the case, if the value we have at the middle index is greater than the target. That means middle value is greater, but we want to insert the smaller value we have gotten in the target. So in that case, we need to look on the left side. So in that case, end whatever we have, we will initialize it, we will update it with middle -1. If this is not the case, obviously it is a greater value, it should search on the right part. So immediately update the start with, middle +1. Okay, once this logic is completed, if at all the value is not found, what I said, start index will be having the index at which the target can be inserted. That means after completing the while loop, we can simply return start index. Okay, so this is the implementation of the, basically the solution in binary searching technique. Okay, so this is the implementation. Obviously the time complexity will be order of log n, and the space complexity will be constant, which is nothing but order of 1 for this approach. Okay, so whenever you are given a sorted array of values which are having distinct values and you will be given a target value, the way in which you should solve this problem is using binary searching technique like we discussed. Okay, now that we understand the algorithm and pseudocode, let's quickly jump in and write the implementation of it and test various scenarios that we have discussed while discussing the problem statement.